I want to take these properties of homogeneous functions now a step further and consider thermodynamic quantities and properties like volume. All right, now as I indicated in the video about homogeneous functions, things like volume that can be expressed in terms of partial molar quantities themselves are homogeneous functions of order 1. I should finish the word function of order 1. Okay, so that means that we can write, for example, that the total volume as a function of the number of moles of each of its components would be equal to the number of moles of component 1 times the molar volume of 1, the partial molar volume of 1, plus the number of moles of component 2 times the partial molar volume of component 2. And remember, based on the definitions of partial molar volumes, this would be N1 times dV dN1 with N2 held constant, and the partial molar with a volume of partial molar of component 2 would be this derivative with N1 held constant. And these are also assuming that temperature and pressure are constant in all of this. All right, so this in fact basically is a direct relation to the Euler's theorem for homogeneous functions of order 1. All right, now we had also written this out in terms of the mole fractions, but if we divided both the total volume and each of these quantities by the total number of moles in the mixture, we would then get a molar volume for the mixture is equal to a mole fraction of component 1 times its partial molar volume and a mole fraction of component 2 times its partial molar volume. But I want to leave it at this for now, because if I'm considering a function here that is a function of just the amounts of moles of the two components, I can write a total differential for this that looks like this. I could write this as a differential with respect to one of those components times the differential change in that component, and a differential with respect to the other component times an incremental or differential change in that component. Now this one has N2 constant and this one has N1 constant. So this is basically just the total differential for volume. Okay, but now what I want to do is, using the homogeneous property of volume, I want to use the fact that this volume can also be written this way. And when I write it this way and take the differential, I would get that in fact this is the differential of the first term, so dN1 times this derivative. Okay, so far so good. Looks just like the term above here. But then I would also have this term dN1 times the derivative, the differential of the second term, which would just be a differential, total differential of this partial molar volume. Okay, similarly for this second term, I will end up with a term that looks like this times dN2 plus a term that is N2 times the derivative, the differential of the second partial molar volume. So all I've done is use the product rule and taking the differential of this expression here, or I could say the differential of this expression here, to rewrite this way. Okay, but now when we compare this to this expression up here, we've got this term present and this term present, so those are present on both sides of the equal sign. So in fact, if we cancel them out on both sides of the equal sign, we would end up with an expression that looks like this. Oops, dV2. So in other words, we have a relationship that links differential changes in the partial molar volumes. Another way to write this is that the partial molar volume of 2 could be written as negative N1 over N2 times the differential in the partial molar volume of 1. I should have left differential there. All right, so this relationship here is a significant relationship because it tells us that these two cannot vary independently. That is to say, the partial molar volumes. if I change the partial molar volume of one component in the mixture, it will have an effect on the partial molar component of the other thing. This is a manifestation of something called the Gibbs-Duhem equation. And this particular version of it relating to volumes helps us understand why when we drew the partial molar volumes, and I'll try to reproduce that picture up here, of both water and ethanol together, and this was a couple of videos ago, ethanol kind of went like this and water kind of went like this. They're mirror images of one another, and that's related to this. Okay, when we have two components of a mixture that are dependent upon their partial molar volumes, we're going to see that kind of reflection effect in the molar volumes of each of those components. All right, well, how does this have a greater significance for thermodynamics? Well, we've noted that, in fact, the chemical potential, mu, is, and I'll say mu for component 1, is in fact the partial molar Gibbs energy with respect to that component. This is with N2 fixed, and we'll say also temperature and pressure. Similarly, I would say the chemical potential for component 2 would be given by this. All right, so these things, in fact, are also, that means that these chemical potentials and, in fact, the Gibbs energy is also a homogeneous function of order 1. So now we can write the Gibbs energy version of this relationship and say that 0 is equal to N1 times d mu 1 plus N2 times d mu 2. Remember, mu 1 and mu 2 are just like, they're the partial molar free energies, partial molar Gibbs energies. So they're like these partial molar volumes. So I just substitute them in there here. And now I've got essentially the Gibbs-Duhem equation for the Gibbs energy. All right, now we've got something that actually is very helpful to us when we consider chemical changes in chemical systems, because it's telling us that the chemical potential here for each of these things are not independent. When one changes, the other one changes in a corresponding manner, and it's based on this sort of relationship. So this, in fact, helps to dictate a lot of the thermodynamics that goes on in processes where we've got multiple components and the amounts of those components are changing. What does that sound like? That's a chemical reaction, or it's a reaction in which we have a solution of two or more components that are being vaporized and forming components in the vapor phase, and that's something we'll talk about in just a moment. All right, but for this, it also has another, I'll say, consequence for this, and that is when we write out our total Gibbs energy as U plus PV minus TS, we can also add a component mu times the number of moles. And the reason we can do that is because now the total differential of this Gibbs energy is just minus S dt plus VdP plus mu1 dN1 plus mu2 dN2, and we can ignore the two terms that would come from N1 d mu1 and N2 d mu2 because of the Gibbs-Duhem equation. So these are the only ones that that are related. And I should have probably included multiple components when I wrote this out down here. So this is a generalization of the total differential for the Gibbs energy that we've seen in earlier lessons, and that help to define changes and equilibrium conditions for a variety of different systems.